Okay. So let's jump back in to this problem we were working on yesterday and maybe recap a little bit. So there will be a problem like this on the final. So just a heads up. I think this is a very good problem and a very good process to understand, right? We're learning about eigenvectors and eigenvalues. Unfortunately, the full applications of eigenvectors and eigenvalues, why these things are important, we won't have too much time for in this class, but we've talked kind of about the applications, and I know a lot of you guys have different majors, so if you're interested in any of those applications, check those out. Or just as well, maybe you'll see it in higher courses. I was talking to one student last night, said he was interested in machine learning, and this was a prereq, and so I'm sure you'll do a lot of matrices, of course, with just computer science and then machine learning as well, especially some of the people I've talked to, like some of the like states, and whenever you have to sort of consider like a state of a system, it's usually stored in some sort of vector, and then as that state evolves based on the information that changes, a lot of those are matrix operations and can model, I think, at least begin in terms of, you know, modeling the decisions or how you can program a computer to make decisions based on how states changes and whatnot. So hopefully this will come up in your future classes and you'll find it useful, and maybe I'll be able to look back and then expand upon some of these. But for now, we still got to get through the basics. So we've seen the straight up calculations of eigenvectors and eigenvalues using the characteristic polynomial. But we started with this example yesterday where the original matrix had some bigger numbers in it. And so our thought is, well, can we somehow make it a nicer matrix? Can we make it a triangular matrix? And we had to be a little careful. We realized we can't exactly do row reductions. This isn't a case where we can explicitly do just row reductions. But our workaround is this application of conjugation, where we have whatever operation we're applying on the left, we also apply that corresponding inverse operation on the right. So what we did was come up with a sequence of row operations. And after we figure out the first row operation we wanted to do, so for example, we started with taking negative row 2, negative 3 times row 2, adding it to row 1. So that was going to be our first elementary matrix, our first row operation. We applied that on the left and similarly applied the inverse on the right. And through this process, we were able to get to a triangular matrix. And that was really nice. And so that allowed us to find the eigenvalues for this matrix. Now, it took us a little while to do it because I wanted to be careful, you know, going through the process, going through each step, made sure we could talk about what works, what doesn't work sometimes, especially these end values that we get to. We kind of saw sometimes when the row operations and column operations can get in each other's way. And so we had to be a little bit more clever in our choices of row operations towards the end of our diagonalization process or triangularization process. But it is actually fairly quick, right? If I had to calculate a characteristic polynomial of this, it would be a pain in the arse, right? We would subtract lambdas, we would have to take a determinant of that, and let alone computing a determinant of that is going to be terribly painful. And then we would somehow have to factor this degree 3 polynomial to find the roots. And so unless you remember the cubic equation formula, which I don't think they teach in high school, you're going to have a hard time. But what we saw here was, well, once you get used to the calculations and can move through them quicker, it really only took us 3 steps. In 3 steps, we had a triangular matrix. And we could get the eigenvalues. And even in those 3 steps, we are now asking this question, well, we just kind of did all this work to get it in triangular. Can we make it even better? Can we somehow get a diagonal matrix out of that? And moreover, what does that tell us? So we went ahead and finished that process, and just one more step, we were able to diagonalize the matrix. Actually, I think I have it written on this page, yeah. And so these were our elementary matrices, and then we realized by conjugating by that sequence of elementary matrices, we were able to get, sorry, that's off screen, we were able to diagonalize our original matrix A. So now not only does that tell us the eigenvalues of A, but where we left off yesterday is now we can actually find the eigenvectors pretty easily. So our previous methods for finding eigenvectors were appending a row by zeros and subtracting off that eigenvalue from that from the diagonal, and then row reducing and finding, you know, a suitable one-dimensional parameter family of vectors to represent that direction, that eigenvalue. Well, now it's actually going to be pretty easy with a diagonal matrix. And so we'll state the theorem after this, but it'll hopefully be pretty clear as to why it's true, or at least give you some insight as to what's going on. So I claim that the combination of all of the row operations that we did, and in this case, it's going to be the column operations, I should say, the operations that end up to the right of our matrix A. If we just multiply out all those matrices, you don't even have to, I mean, you can ignore the inverses and think of them as the inverse of these matrices if you want, but really each of these are going to be matrices in and of themselves. If we multiply them all, that is going to give us our eigenvectors. Moreover, I should say we call this P, is standard notation. And so this one, I think we call this guy P, and this one P inverse. Or it doesn't matter. We could call this one P inverse and this guy P. As I've kind of stated so far, the P and P inverse, whichever one you want to label as which, not terribly a big deal. And especially since we have inverses here, let's call this guy P inverse now. But it is going to be the one on the right, the product of all of those terms on the right, that gives us these eigenvectors. So let's go ahead and rewrite these out. So we finished writing down our elementary matrices we applied. Let's go ahead and write down the inverses. And now the other nice thing that we saw with these computations is that they are only matrices of type 3. You can use matrices of type 1 and 2, but you don't need to, especially type 2. What is type 2 going to do? It's going to just switch the rows. Or sorry, is it type 1? I think that's whichever one switches the rows, right? If we switch the rows, well, the action on the right is going to switch columns. And really all that's going to do on the end is going to give us still a diagonal matrix. It's just going to change the order of the entries of the diagonal. Doesn't matter, right? All we need is what are the distinct numbers on the diagonal. It doesn't matter what order they're in. And again, since we're not actually row reducing, we don't need ones. We're not looking for those ones on the diagonal, so we don't have to scale anything to get those ones. So no reason to, multiply by a row by a given factor. So all elementary matrices of type 3, and the nice thing about elementaries of type 3 is it's always ones on the diagonal, and then whatever entry is non-1, you just change the sign, and that's the inverse. So easy to come up with the operations in terms of elementary matrices and the inverses. So these are good problems for the exam as well. It kind of covers a lot of the stuff we've covered so far. Primarily row operations, inverse matrices, elementary matrices and their inverses. So this is kind of like one problem of this means I don't really need to put any problems on the final from the first section, from our first week, since we're essentially re-going over a lot of that stuff. The other thing I want to say is that if you want to be a little more shorthand, if you ever leave blank spots in a matrix, consider those zeros. So if you just get tired of writing all the zeros, especially with these elementary matrices, be careful with your positioning. But if you write a matrix like this, It's usually implied that the blanks are zeros. That's another little time saver you could do when you're going through this process and doing all the calculations. So those are our inverses. We want to multiply them all together. Be careful of the order. You want to make sure they are in that same order. And then that will give us this P matrix, and we'll see why it gives the eigenvectors. So let's go ahead and multiply those out. Again, our E1 was 1, 3, 1, 1. Our E2 inverse was diagonal with a 2 there. Our E3 inverse, diagonal, had a 2 here. And then E4 had the top right as a 15. So that's E1 inverse times E2 inverse, E3 inverse, and E4 inverse. So however you want to multiply these, you could do it 2 at a time, do like those 2 and those 2, or you could just do them consecutively. So here's how I want to do it. Since these are row operations, now, right, if I consider this matrix acting on that one on the right, it's a row operation. So what's going to happen here? We're going to have this matrix, and then I'm adding 2 times row 1 to row 2. So row 1's not going to change, but then I'm taking twice that to row 2. We can bring that guy down, and then what's this guy going to apply to here? This is just 2 row 2 added to row 3. So our result, row 1's not going to change, row 2 isn't going to change. But we are taking 2 times row 2, adding it to row 3. It's going to give us a 4, a 2, and a negative 59. This one is looking like it might be a mess. Usually these don't end up too terribly. Even though the numbers in A were kind of a mess to start with, usually the eigenvectors aren't too bad. That row's a little iffy. We'll see what happens. And then our last one, we are adding 3 times row 2 to row 1. And so that's going to mess a lot of things up. So 2, 1, minus 30, 4, 2, negative 59. And then we want 3 times this plus row 1. So that'll give us a 7 here, a 3 here. And then that'll give us 90 plus 15 is 105. And this was a 59. And double check. As long as I wrote these guys down. Did we have all negatives on our E's? Let me double check the old notes. Always good to check as you go as well. Yeah, the 15 was negative on the right. On our left, all the constants were negative. Yeah, that's kind of what made that last column bad. Was just the fact that these constants were the same, so we didn't get any good, additions and subtractions canceling off to make the numbers more reasonable. But is what it is. And so this is going to be our P inverse. And so get another page. Our P inverse we saw was 7, 3, 4, 3, 1, 2. And our last column was not pretty. But luckily the eigenvalues are also not too bad. So maybe doing the multiplication won't be terrible. Actually, no, the original matrix was a mess. Okay. Let's rewrite A. It was 33, 105, 105, 10, 28, 30, minus 20, minus 60, and minus 62. Just for posterity as well. So since this guy's going to be on the right, let's go ahead and find P. So how do we find the P term, the conjugate on the right, on the left, excuse me. So we just multiply all of the non-inverse elementary row operations on the left, and just be careful of the order. Now we're starting at 4, we're going down to 1. So let's go ahead and multiply those out real quick. 1, 1, 1. 1, 1, 1, and we had a minus 2 here. We have 1, 1, 1, minus 2 here, and 1, 1, 1, minus 3 was there. And so that's our E1, E2, E3, E4. So I'm going to multiply in the same way. This one says take negative row 2, add it to row 3. So we're going to take this matrix, still have that guy, still have row 2 the same, and then take negative row 2, add it to row 3. Fill in the zeros if you want. I'm going to apply that matrix now. And this says take negative 2 times row 1, add it to row 2. So row 1 is going to be the same. Row 2, I'll have a minus 2. That'll be a 6 and 1, so we'll have 7. And we'll have 0, minus 2, 1. Third row doesn't change. And then our last one, now I've got 15 times row 3 added to row 1. So row 1 is going to change. Luckily, that first entry is not different. We will have negative 15, and 3 is negative 33. And then we've got 15 and 0. So minus 2, 7, 0, 0, minus 2, and 1. And so that's our P. Oh, sorry, I was off screen there. Everyone got it? All right, so let's go ahead and let's come back to this page and write our P was 1 minus 33, 15, minus 2, minus 7, 0, 0, minus 2, and 1. So we did all that work. You should want to check a little bit, do a few checks just to make sure. What are some things we could do? Well, we found P by actually doing the computation of the row operations. It's a better way to find P rather than one computing P inverse and then finding the inverse of that. Going to be a pain to use our typical methods. Since we already know the combination of elementary row operations, we can do them in their reverse. It's easier to just multiply them on both ends. So you could multiply these two matrices, check to make sure that they are inverses. That should follow, of course, as long as you are comfortable with the fact that you're right here. I don't know if we can get some of it on screen. So here was our P calculation. Here was the beginning of our P inverse calculation. And you could see that if I just multiply these matrices, well, the middle two, those are going to cancel. That'll be the identity. So we'll have the identity in the middle, and then that will identity multiplied by anything gives us that same thing. So then now we can move on to the next two and see if when we multiply those two, we get 1. So that should work, and that's at least a way to check to make sure we're doing these calculations correct. We want to check to make sure our eigenvalues are correct, which I guess we haven't really shown. Is we want to make this claim that now these rows are our eigenvalues. Maybe that's not the best notation using E. Let's since we were using E for our elementary matrices. Let's just use V for our eigenvectors. And one more thing, let's put on the sheet that kind of summarizes everything we got. We've got our A, P, P inverse, and maybe we'll write down our D. So the D is the diagonalized version of A. And so our eigenvalues were 3, minus 2, and 2. So this should be the eigenvalue. I don't even know if I like E using those. Let's call it just V. V3, V minus 2, and V2. You can call them whatever you want. I'm actually choosing the subscripts corresponding to the eigenvalues. You don't have to, but it kind of just hints at our intuition that this vector should be an eigenvalue of 3. This vector, column vector, eigenvalue of minus 2. And likewise, this eigenvector should have an eigenvalue of 2. And so let's kind of go through what's going on here. If our math was correct, we should see this equation hold. And so when you think of A acting on P, well, what is our matrix multiplication of this matrix acting on this matrix going to do? Well, if you actually do the entries column-wise, so it's going to be the first row, first column, then the second row, first column, third row, first column. Well, that's really just the matrix A acting entirely on the first column, namely the matrix A only acting on V. And then likewise, you can kind of move over to the next column and then move over to the third column. So really what matrix multiplication is, since we want to consider this P inverse as 3 vectors formed into a matrix, it's kind of just an organizational way of organizing those 3 vectors into one algebraic structure. And then now we've encoded in our matrix multiplication, we've preserved this algebraic structure. Namely, it's kind of like a commutativity law. It's the same as A acting on the first column, A acting on the second column, A acting on the third column. And so let's kind of isolate those. If we want to take a look at A, unfortunately, these numbers are not pretty. So let's just do 1, maybe 2. And then I'll leave the rest to you guys to check. So this is our matrix A, and if we act on the first column, our 7, 3, and 4, what are we going to get? So we're going to have some arithmetic to do here. Let's see. So 33 and 7 gives me 210 and 21. Excuse me. So 331. And please check me if I do any of these multiplications wrong. I usually try to tell you guys if you're multiplying, as long as the total number of digits multiplying is less than or equal to 4, you should be able to do it reasonably well mentally or with scratch paper. As soon as you multiply and the total number of digits is 5, so 3-digit times a 2-digit, or a 3-digit times a 3-digit or more, then usually those are calculator problems. So on exams, I will not give that big of numbers. There are going to be some 2-digit matrices where you're going to look at it and know you should probably not calculate a characteristic polynomial. That row operations will be easier. And then, of course, you still got to check. So what do we get? 700 plus 35 is 735. Oh, no, sorry. I'm doing the wrong multiplication. 3 times 105 is 315. And then 4 times 105 is 420. Hey, all right. And then let's see, we'll have 70. 3 and 28 is going to be 60 and 24, so 84. And then 4 and 30 is 120. We've got negative 140, negative 180. And then let's see, negative 248. And did I miss something? Something can't be right. So what are we expecting to get? We should get a 3 times that. So this result should be 21, which it's definitely not 21. Boy. So this is the problem with these problems. You make one little mistake, and then all is lost. All is lost. Let's double check. Let's triple check everything. So the matrix we were working with.
Shouldn't the negative 14 be negative 140?
We're at, sorry, I don't have the chat open.
The negative 14.
Negative 14, negative 140. Here, yeah. That doesn't help us though. I'm actually just still looking at the first column, but so that's good. One mistake. I feel like one of these terms should be negative, and I'm wondering, like, did we miss a minus sign? Did I forget to just write it? Let's go back. So that's the correct matrix. And if we let's check our diagonalization. So this is a problem in the book. I don't think I did it the same steps as the book, but it looks like, okay, we're getting the same eigenvalues. 3 minus 2. Uh-oh, should we have a minus 2? Let me see. Yeah, we are off somewhere. Oi, these are such a pain. This one has been a pain. Okay, so the one on the exam should work out, and the numbers aren't as bad. We need to take a break from this problem and come back to it. So maybe we'll leave it as a little bit of a homework problem, since we've been working on this problem all yesterday. Hopefully the process makes sense. So our steps now would be we need to go back and check. And so through this check, something went wrong. This is clearly, I mean, this 734 is clearly not going to be an eigenvector of this matrix, because we expect it to have a multiple of 3. So we should expect to get 21, 9, and 12. And that's not how these numbers are going to work out. So something went wrong, and it could be a matter of a minus sign in one place, and then that minus sign in one place makes some of the numbers way larger than what they need to be. So we'd have to go back through and check. Unfortunately, I do not want to do that at the moment. So I don't want to do this live in class. I'll look over it after class and try to see where our mistakes are, and then we can go back over this before the exam. But hopefully this process makes sense. And so the idea is that if we have PAP inverse equaling to a diagonal matrix, well, it's essentially saying that PA is going to be the diagonal matrix times P. And the diagonal matrix times P, it's simply going to change each of the corresponding columns, and it's going to scale the columns by that given multiple. So in some sense, this is kind of saying that A is going to behave similarly on P inverse. That A acting on P inverse is just going to scale the columns of that matrix by the given scaling factor that we have in the diagonal matrix, meaning that if we're just getting a scalar multiple of that column vector, then that column vector will give us the eigenvector. So that's that result. Let me clean this up and I'll take a look at the computations, and then maybe we can talk about it in a future date. For now, we do got to move on with some material. So homework assignment as well. Look over all these steps we've done. See if you guys can find the mistakes. Good practice finding mistakes. It'll help you find your own mistakes. And I kind of, as I was saying, it looks like we're close. I mean, we got the correct eigenvalues, but it looks like some of these, in getting rid of the zeros here, the book doesn't completely write out all the steps, but it looks like we have some things that might be a little wrong. So take a look at that, see if you can find the mistakes and see if you can correct it, and then check to see if your eigenvalues are correct. Okay. So let's kind of summarize some things. So given a matrix A, we can, let's just say, of course, n by n, we can find eigenvalues by looking at our characteristic polynomial. So determinant of A minus lambda I equals 0. And then moreover, find the vectors by simply taking a look at, again, A minus lambda I, and then now multiplying it by some vector and setting that equal to 0, the 0 vector. And then, of course, we can solve for the components up to one, at least one free parameter, to find the corresponding vectors of that eigenvalue. So this was method 1. Sometimes method 1 is hard. Method 2 is to perform row and column operations on A sequentially by conjugating with elementary matrices. So that process we saw, we just started with A, and then we conjugate, and then we just keep doing that until we get a diagonal matrix. Or I guess we shouldn't say a diagonal. Sometimes you won't get a diagonal matrix. Get as close to a diagonal as possible. So at least if you can get a triangular matrix, you can find the eigenvalues pretty easily. And then if you can't diagonalize it, sometimes you're left with some things that you like, some extra ones or some extra positions that you literally cannot diagonalize, mainly when the eigenspace of a given eigenvalue is going to be less than the dimension or less than the multiplicity. And so we'll state that in a second as our theorem. So the other things we kind of want is to, if diagonalizable, then there exists a matrix P. So in our previous notation, we actually had this P inverse of, we'll call it X1. Actually, not even, no commas there. Sorry, this is a matrix where the xi are eigenvalues or eigenvectors. And what we were hoping to show with the last example, that this P inverse that we found through process 2 actually gave us the eigenvectors. Unfortunately, by checking ourselves, we realized there's probably a calculation mistake somewhere in there. It might even be as simple as just one mistake, and one minus sign could have been throwing all of that off. So other questions we want is, so we can find P. I can find P inverse by the sequence of elementary matrices in method 2, or, and so this is the other technique, is to use method 1 and then find eigenvectors first. And then check diagonalization. Does that make sense? So two ways we can kind of approach the same problem. The method we were just using was, let's try to diagonalize first. That will give us the eigenvalues. It will give us the eigenvectors in this inverting matrix. Or I guess we could call P the diagonalizing matrix. And then we could check to see if it does indeed give us a diagonal matrix, check to see to make sure that the vectors we found are in fact the eigenvectors. But sometimes, of course, if you're given a nice enough matrix, if the matrix to begin with is small enough numbers, not a very large matrix, maybe a 3x3 or less, then sometimes this method is a little bit quicker. We can actually do this method first, and then problems might ask us to find this P inverse. So there could be a question like that on the final. I don't want to spend time doing that because I kind of want to wrap this up. But good example in the book that I can point you towards. Is just example 7.19, where they give us a matrix A. And nicely enough, we actually have a lot of zeros here. So finding the eigenvectors or eigenvalues shouldn't be too hard. If we want to just subtract off lambdas from the diagonal, expand the determinant or about the first row, kind of quicker to find the eigenvalues. Finding the eigenvectors is a bit tedious, as we saw last week. This was last Thursday when we were doing the individual eigenvector computations. Once you know an eigenvalue, it's a matter of just doing that many row reductions. So however many distinct eigenvalues you get, you've got to row reduce the matrix when you subtract off that eigenvalue from the diagonal. So that can be a little tedious. But from that process, you can find your P and P inverse. So that PAP inverse is D. And again, I think the book actually switches it. The book labels this one as P inverse. Again, doesn't matter what you call them, as long as you know which matrix goes on the left and which one goes on the right. Sorry, what'd you say? Was there a comment? Okay. So check those. Let's write down some of the remaining theorems we have. So, theorem. So let's A be our n by n matrix, and let's say we have lambda 1 up to lambda m are distinct eigenvalues with, let's say, the set of x1. Let's call this set just capital X up to xm eigenvectors corresponding to each lambda. Then this set is linearly independent. So any eigenvector that has a specific eigenvalue, if you were comparing two eigenvectors and they have different eigenvalues, they're going to be linearly independent. And not only that, if I'm considering a set of eigenvectors and each eigenvalue corresponding to the eigenvector is distinct, then that set is linearly independent. We saw a little bit of a hint at this on the exam, where we were taking a look at something like A of u equals 5, A of v equals 7, sorry, 5u and 7v. So I think that was a negative 7 actually. So u and v are eigenvectors, but then the question was something like, is u plus v an eigenvector? You had to think about why. With 2, it's fairly easy. So you have to kind of do a little bit of work. We want to show that they are linearly independent. Because if they were linear for 2, should be fairly easy. If they were linearly dependent, then that means they would be in the same subspace, meaning that they would actually have the same eigenvalue. So since they have distinct eigenvalues, you can show fairly easily that they are linearly independent. And then moreover, now if I take a combination, a linear combination of distinct eigenvectors with distinct eigenvalues, do we get another eigenvector? The answer is no. Because we're actually kind of skewing the subspaces. These subspaces spanned by each individual eigenvector is that characteristic dimension, that characteristic direction. And as soon as I start taking combinations of those directions, now we're not in one direction or the other. And so it's not going to be one of these characteristic directions. So take a look at that problem again and try to like justify it mathematically and see how it ties in with this theorem. Corollary to that is if A has n distinct So of course, A is an n by n matrix. So if we have fully n distinct eigenvalues, lambda 1 up to lambda n with vectors x1 up to xn, then A is diagonalizable. I don't think there's an E there. Diagonalizable. And the set of eigenvectors form a basis. So of course we have n distinct linearly independent vectors. It's going to form a basis. And that is nice. It's nice when we can, again, bases are the ways we model our space. It's kind of the way we scale our space and relate all vectors back to those bases as linear combinations. And so if we can actually model the space as a collection of eigenvectors, it's kind of nice. It gives us some easy computational rules and computational tools in terms of the linear transformation we were working with. But there's some conditions here, right? We have to have distinct eigenvector values for that. And as we've seen, sometimes we don't have distinct eigenvalues. And so what happens when we don't? And this is a little bit of a problem. So let's take a look at another example, and hopefully this one won't take us too long. It's going to be similar to something we saw on the exam. Let's pull out a baby version. So in question 6 on our last week's exam, we saw a matrix where it was already diagonalized, or it was triangularized for you. It was a triangular matrix, almost diagonal. And this is actually a deeper result in mathematics, that even if a matrix isn't diagonalizable, you can actually make it almost diagonal where the eigenvalues are on the diagonal, and you can put like ones on the off diagonal. And what did we see with this one? So the question was, are characteristic polynomials pretty easy to compute? It was just minus 2 minus x, and then this one will be 4 minus x squared. And the example on the exam, we had 2 sevens, so it was a 5 by 5 matrix, and then zeros everywhere else. So characteristic polynomials, pretty easy to find. It's pretty easy to determine our lambdas, so our eigenvalues, but there's only 2 eigenvalues. And part of the question on the exam was to determine the dimension of the eigenspace. And the way we would traditionally do that would be we have to take a look at our characteristic equation. We would have to take a look at, so let's take a look at what's going to happen with 4. As I've said, with distinct eigenvalues, if they only appear once and have multiplicity 1, dimension 1. That's all it can be. We know there's going to be one eigenvector that corresponds to that, namely the E1, 1, 0, 0 is going to have an eigenvalue of minus 2. So we know that the dimension of that eigenspace has to be 1 and can't be bigger. But the eigenspace of 4, we got to be careful with. It can be up to 2. The multiplicity of the root is 2, but that doesn't necessarily mean the eigenspace is multiplicity 2. Or has dimension 2. And so you want to take a look at a minus 4i times a vector v equals 0. So we're going to solve this and see how many degrees of freedom we would get for such a vector. And so, of course, solving such a thing, not terribly difficult, especially with a diagonal matrix. Since we're subtracting off 4s from the diagonal, it's just going to leave us with this matrix. Sorry, actually, if we were doing row operations, we would append a row of zeros or a column of zeros to try to find our solutions. But what do we see? This guy has since it's essentially already diagonalized for us, it's already row reduced for us when we subtract off that 4. But the rank of this is rank 2. And then that means our nullity is 1. In other words, the degrees of freedom if we were to solve this as a system of equations and use a parameter, we only have one free parameter as 1. This implies that the dimension of the eigenspace corresponding to 4 is just 1, since we only have that one free parameter. So even though the multiplicity was 2, we only have the dimension of the eigenspace is 1. So it's kind of unfortunate. And well, what that should tell us is that we actually only have 2 eigenvectors. We have an eigenvector for -2 and one eigenvector for 4 and no other eigenvectors, which means we cannot create a basis of eigenvectors. And so if I cannot create a basis of eigenvectors, how are we going to create that inverting matrix? So if we think about this question in terms of, can we find this P such that PAP inverse is diagonal? Well, by our previous theorem, what did we need? If we can find it, then that matrix we find has columns of eigenvectors. So it's an if and only if statement. And since we only found 2 eigenvectors, and this has to be 3 by 3, so that P is a 3 by 3 matrix. So P does not exist. By the previous theorem. So try it if you want. Play around with it. Try to see what would happen if we tried to diagonalize it. Try those elementary row operations and peck around. I would guess that this is literally the most simplified it could be. So try it if you want to try any sort of row operations. What you'll find is because we're conjugating, it'll actually just make the matrix a little more complicated, or at least equivalently complicated. It's kind of like one of these, it's like a Rubik's Cube almost, with one of the pieces pulled out and flipped around, which makes it impossible to solve. So you can try to do some permutations with some elementary matrices, but you'll kind of see you'll either just make it more complicated or equally complicated, but you'll never be able to fully diagonalize it. And that's kind of, it'll give you some insight as to what's going on with that previous theorem. And so what is the crux? What is now the concluding theorem? Previous theorem was nice, but it only dealt with the subset. I do know that at least the 2 eigenvectors we find from these 2 are going to be a linearly independent set. It's just that we can't form a basis out of them. We could expand, we could add on one other vector to be a basis, but that extra vector we add on isn't going to be an eigenvector. So we cannot form a basis of all eigenvectors. And so when can we, what is the real result we're going to be learning from this is that a matrix is diagonalizable if and only if for each, let's say, for each eigenvector, or say eigenvalue, lambda I, with multiplicity, let's call it ki, then, or would say so the dimension of that corresponding eigenspace is full, meaning the dimension of the eigenspace is as maximum as it can be, which is the multiplicity. So distinct eigenvalues lead to eigenvectors that are linearly independent. So if we have all distinct eigenvalues, it's nice. Then we're basically guaranteed that it's diagonalizable. But if we don't have distinct eigenvalues, what we really are hoping for is that the multiplicity, whatever multiplicity of the eigenvalue is, we get that many eigenvectors, at least linearly independent eigenvectors corresponding to that eigenspace. And so in that case, so if we kind of make another similar matrix, kind of like on the exam, if it is diagonalizable, even though we can have repeated numbers, as long as there's non-extra numbers like ones that end up on the diagonal, you would see that we do have three distinct eigenvectors for this, namely E1, E2, and E3. All linearly independent eigenvectors. And even though E2 and E3 have the same eigenvalue, they're linearly independent. And so the dimension of that eigenspace of 7, the eigenspace corresponding to 7, is 2. Okay, so things we need to conclude. Kind of wanted to talk about trace. We wanted to talk about multiplicity and raising a matrix to a higher power. So let's kind of started our application section. So suppose we have an n by n matrix with a diagonalizable. Diagonalizable. Sorry, put those in there. Then, if we want to compute something ridiculous like a high power of a matrix, right? A to the 50th is just A times A times A. Since it's a square matrix, we can keep multiplying it. But also, since it's diagonalizable, that just means it's going to be P D P inverse raised to the 50. But when we take a look at this guy raised to the 50, it's just going to be PDP inverse times PDP inverse. And you're going to keep doing that 50 times. But pairwise, when you look at consecutive ones, when we have P inverse times P, that's just going to be the identity. So we would combine these two, and it's just P D squared times P inverse. And then, of course, we still have the product of the rest. And every time you're going to do that, what's your net result? It's going to be something like this. So if we want to raise a matrix now to a higher power, it's nice when they're diagonalizable, because raising a diagonal matrix to a high power isn't too bad. So let's suppose we have a diagonal matrix. At least in terms of shorthand notation. Of course, we don't want to actually compute out something to the 50th power. So minus 1 to the 50th power is going to be 1, but then it's just going to be each diagonal entry raised to the 50th. And you don't have to compute those out, but it's easy enough to write them in terms of some sort of algebraic operation, 2 to the 50th, 3 to the 50th. And then if we had our P matrix, we could then multiply those out, of course, keeping those as 2 to the 50th and 3 to the 50th. So that's raising to higher power. I don't really want to go through many examples with that. Maybe check out any of those computations in the book. So sometimes the first step might be diagonalizing the matrix first, figuring out those steps, and then raising things to the highest power. So take a look at example 727 for the computations on that. The last thing I want to state, and I'm not sure if this is in the book, but it is very important. So the determinant, so hopefully you can at least gather that even if we can't diagonalize a matrix, we can at least triangularize the matrix. So that you'll have to take my word for it. We don't really have time to prove that. But as we kind of saw in those previous examples, where even though A is not diagonalizable, but what you can show is that A is going to be similar to B, where B is going to look like some pairs. It's what's called Jordan normal form, where it comes with like ones on sort of paired entries. And if we did complex eigenvalues, we could do this a little bit more. Unfortunately, this class is just so rushed over the summer. A lot of good stuff we're leaving out. So for example, we saw this matrix. Now, this is not diagonalizable, but sometimes we start with a matrix and could end up here. So suppose we started with some matrix and then we tried to diagonalize it through those elementary row operation methods. Here, let me rewrite that. So we start with some matrix A, we try to diagonalize it. We know we can at least get a triangular matrix. And so with our elementary row operations, we can at least get it in this form. Yeah. And by our multiplicity, or our multiplicative property of the determinant, this tells us that this act of conjugation preserves the determinant. I think we stated this in a theorem. Didn't quite prove it. It's as simple as remembering that the determinant of the inverse is 1 over the determinant. And so now, since we're in a commutative ring where multiplication commutes, we're just going to get the determinant of A. So if you believe this fact that even though if A is not diagonalizable, we can at least put it into a triangular matrix where the diagonal entries are still the eigenvalues, then you should believe that the determinant of A is the product of all the eigenvalues. Not necessarily distinct. So some of those could be repeated, right? In our previous one, it'd be minus 2 times 4 times 4. Moreover, the other operation that I've been talking about, unfortunately, we haven't gotten to use much, so I do want to use it, is the trace operator. And that we learned that the important thing of the trace, so recall that the trace of a matrix is just the sum of the diagonal entries. And moreover, that the trace is going to be invariant under conjugation. Since even though the multiplication, matrix multiplication does not commute, we cannot switch the order in general, the commutativity or the anti-commutativity doesn't affect the trace. So I can switch two of them as long as we're computing a trace afterwards. It's not going to affect the trace. And so we're still going to get the same trace of the original matrix. So conjugation does not affect the trace. And so what does this show? Well, no matter what matrix I start with, if I add up all the diagonal entries, it's going to be the same as if I diagonalized the matrix or attempted to diagonalize the matrix and then added those diagonal entries. And we know that those diagonal entries is going to give me the sum of the eigenvalues. I guess we should say n here, since if we get it as close as possible, we will have an n by n matrix. Some of the eigenvalues will be repeated. So this is the sum of eigenvalues. So you can use this as shorthand a little bit. Let me see if we can find a decent problem to demonstrate this. We don't have much time, and I did want to get to orthogonality today. Of how we can use this, let's just maybe try a 2x2 matrix. And let's pick reasonable values, hopefully. Let's do, I don't know, 4 and 3 and 2 and -1, something like that. And so our goal, problem statement, might be something like find the eigenvalues. And we've seen two different ways of doing this. We could 2x2, not too bad, computing the characteristic polynomial. We could try to do some elementary row operations. Again, 2x2, not too bad. But the other thing we could do is simply compute our determinants. So our determinant of A is going to be, let's see, 12 minus 2 plus 2 is 14. And moreover, the trace of A is just going to be the sum of the diagonal entries, so 5. So this tells us that if we have two eigenvalues, that lambda 1 plus lambda 2 equals 5, and lambda 1 times lambda 2 equals 14. So it actually gives us a little bit quicker way of computing things. This is why the determinant and trace are both very nice operations on matrices. Unfortunately, solving this looks like it's going to be difficult, and it's nonlinear since we are multiplying these two. So, and it looks like the numbers I chose were not actually very helpful since we're getting prime numbers and 14s. So you could do something like lambda 1 is 14 over lambda 2. And so we've got 14 over lambda 2 plus lambda 2 equals 5. And then solve from there. So the quick way, the slightly improper way, is to just multiply everything by lambda 2. And so you come up with your equation. And unfortunately, it doesn't look like that's going to factor for us. But if I had worked out an example beforehand, sometimes we can work out easier cases of this. Now, I am leaning towards putting a problem like this on the exam, so I did kind of want to show this to you guys and potentially warn you, because the other thing we could do, or I could give you some sort of matrix which is a 3 by 3, or A11, A12, A13, etc. I could say things like, given that, say, lambda equals 2 is an eigenvalue, find the other two. And there's a couple ways to do that. Well, what do we need? We need a system of equations. And so if there's 3 unknowns, potentially 3 eigenvalues, right? We already know one of them, which means we need 2 other equations to solve in order to solve for the other 2. So a quick way to do something like that, especially if you can, sometimes there's a matrix that's like, maybe there's an entry here and then zeros everywhere except here, and you can kind of pick out one eigenvalue easily. Finding the other 2, you can also find pretty easily by understanding that the determinant is just going to be the product of these guys, and the trace is going to be the sum. And since we know that, let's say lambda 1 we know is 2, we can plug in 2's there, and then use the resulting equations for whatever we compute the determinant and trace to be to solve for the other eigenvalues. So it's another kind of quick shortcuts that the trace and determinant calculations can give us in terms of eigenvalues. Any questions? So that is it for spectral theory. Let's go ahead and move on. Let's take a look at orthogonality. We want to get to the Gram-Schmidt process. So everyone take 30 seconds. Let's take a quick break. We've got about 15 minutes.